Section 19.2 talks about the topic of resistance. So this goes hand in hand with what we talked about yesterday. What was yesterday's whole idea about? What was the topic, the main idea? What did we look at? Think back to what it was called.
Kind of like the currents and how everything relates, and the speed and all that.
Yeah, current, the flow in the system, the speed of the EM fields. So we talked mainly about current yesterday. So current we think of as like a flow. Now, if you had water flowing down a river and you wanted to harness the power of that water, what might you build in that river?
Yeah.
Build a dam, yeah. And a dam, what it does is as the water flows through, it turns some sort of an axis or a crankshaft, which in then turns something else which generates some sort of power. That power, hence generator like we talked about yesterday, that power is then converted to electrical energy, and as a result it can be used in the local town or wherever it may be. Same idea occurs with a windmill, right? Except instead of harnessing the power of water, it harnesses the power of wind. So with resistance in electrical circuits, what we're really doing is very similar to that. We're taking our current and we're regulating our current. And the current in the system flows freely if it's not regulated. So if you attach a wire to one end of a battery, and Kev, you probably, Marcelino know this from what you guys have been working on, and attach another wire to the end of the battery, what you'll get there is you'll get like a short circuit, it's called, and that wire will have flow through it, and it'll heat up, it'll get really hot, because there's nothing there to slow down the flow or regulate the flow of current. Now, if you suddenly attach a light bulb, the light bulb is a resistor. Resistance, the same name again. And that resistor regulates the flow of the current and actually utilizes it. It converts the electrons and their energy into electrical energy, into light, when you see it with a light bulb. Depending on what the application is, it's not necessarily going to be a light bulb. Now, that's an example of a resistor that we're going to talk about in this class. Another example could be like an air conditioner or anything you literally plug into a circuit. Anything you plug into a circuit to use energy has to have some internal resistance. And that resistance is what allows the flow to be regulated and to use that energy. Okay, so resistors, not only are they in circuits to use energy, but they're also there to regulate the flow in that circuit. Have you ever looked at if you look at a computer board, you'll notice that along the computer board, and we're going to see this actually, along the computer board itself, there's these little cylindrical things with rings of color on them, and they act as resistors. Okay, so those resistors there regulate the flow. So if you don't want the electric current to be a certain value, you may add or replace resistors accordingly. Jake, make sure you're focused. So if we have, two resistors in series versus two resistors in parallel, we'll learn in chapter 20 about what that really means. Okay? So in this idea, we're going to calculate the current, the resistance, and the potential difference. And we're going to do that using Ohm's law. So then we're going to distinguish between materials that are ohmic and non-ohmic. And all that means is it follows the predictable pattern. And then we're going to talk about things that affect resistors, and then something that's called a superconductor, a small or short application of them. So let's first look at the term resistance. As we talked about with water flow and a dam, similarly here, resistance is the opposition to flow of current in a conductor. Okay, the opposition of the flow of current as opposed to the flow of water or some other, fluid or material. Voltage. Now, voltage is, what do you think of when you hear voltage first? I'm curious. What's the first thing you think of? Strength. That makes sense, right? Voltage, strength. What else? This is good. What else?
Like watts of electricity.
Okay, watts, which is power but related to voltage.
Yeah.
Strength, watts, power, good. All these things are related to each other. They're not all the same thing though. They're not really interchangeable. So let's make sure we're careful. Okay, so before I ever took physics, when I heard voltage or power, I thought they were always the same thing, right? Like power, voltage, energy, they all sound the same. But they're not. Voltage is a little bit different than energy. Energy is different than power. Power is different than capacitance. These are all different things, actually, although they're used a lot interchangeably because most of them are directly related. The more voltage you have, the more power consumption you're probably using. So yeah, they're directly related, but they're not the same thing. Okay? So voltage. Voltage is really what's called a potential difference. A potential difference. So remember how we looked at the potential energy between two charged particles? We said PE equals, it was K, Q1, Q2 over R. And that gave us the amount of difference in potential electrical energy between these two different charged sources, or a charged source and a test charge. Well, in this case, we're looking at the potential difference again, like we did there, but the potential difference between the different terminals. So in a battery, you have your positive terminal, your negative terminal. Those are connected to a wire. That wire is connected to some sort of an element, whether it be a light bulb, a generator, something. And then that's connected back to the negative terminal. So you start at the positive, go to the negative. The difference in energy across that, the amount of energy that those charge carriers are using as they go through the circuit, whether they gain or lose charge, is really what you're looking at for potential difference. So a 9-volt battery simply means that the one lead has 9 more volts of potential than the other does. And volts are a measure of voltage or potential difference here. How many volts do you get from an American outlet? 120, good. 120, so you knew that right away, good. Anybody know about outlets in other countries?
Isn't Europe 220?
Yeah, it's either like 220 or 230, I forget which one it is. I know that in the US we have some 220 outlets here for things like air conditioners. They run on 220 for the most part. But yeah, in Europe it's 220 or 230, 240, I forget actually, if somebody wants to look it up, because the other class we weren't even sure. But it's something in that range. So the amount of voltage changes. Now, if you have too much voltage and you connect something to it, what's going to happen?
Wouldn't that kind of like lower, like if you were to plug in an air conditioning to like 400 voltage, then wouldn't it just kind of stop working?
Yeah, it would overpower in a sense, okay? It would be like a surplus, like a surcharge of energy. When do you get that? You get that during storms. Why do you have a surge protector? Because a surge is exactly that. A surge is too much energy for the circuit to handle. So a surge protector automatically trips off when a certain amount of energy is coming through, or a certain amount of voltage or current. They can be measured either one, really. So a surge protector prevents you from something like that. Let me think about what else with voltage.
How come they have like different shapes for different countries? Like the...
Personally, I don't know, but I think, and this is a question last class that I kind of brought up myself, I think it's so that you don't accidentally plug your outlet into it. Because if they're running on 230 and we're running on 120, and you just plug in directly with an American prong or outlet, you'll get a surcharge and you'll probably blow your actual CPU or something in there, the battery, whatever it is. But what you do is you put an adapter. What does that adapter do? It regulates the current. It changes the amount that's coming through a voltage too. So when you attach that adapter, it's not just changing the shape, but you're actually using the internal resistance of that adapter to regulate the amount of flow coming through the circuit. Okay? So if you think about it, well, I'll leave it at that for now, because we're going to get into more voltage and circuitry in chapter 20 and 21 and 20-2. There's a lot that this is related to, but I don't want to jump ahead too far before we know the theory behind everything. The next thing. So the next thing we're going to talk about is called Ohm's law. This is very similar in nature to Hooke's law. Why is that? Why do you think that this would be similar? Why does this look similar to Hooke's law? What was Hooke's law? What was Hooke's law? Anybody remember Hooke's law? The law for springs. F equals... That's potential energy for springs. Potential energy. But what's Hooke's law with force? Force equals...
Time. Distance? No.
Yeah, constant times distance. That's fine. Kx. Constant is k. Distance is x. Hooke's law was F equals negative kx. It's the amount of force stored in a spring when it's stretched or compressed. Well, look at this one. The force is like the voltage. And in this case, it turns out, we have I and R. I from yesterday is what? Current. V we know as voltage. We just saw that a minute ago. We talked about voltage. R, in this case, stands for resistance. So what we'll notice here is that Ohm's law tells us the product of current and resistance is what gives us the amount of voltage that's acting across that individual element. So if you know, like an air conditioner, has an internal resistance of a certain amount. You know the amount of current flowing through the system. You can figure out the amount of voltage used by that actual air conditioner. Okay, now you can also figure out the resistance of an object by knowing the voltage and the current. And if anybody, some of you I know for a fact have used one, but some others may not. If you've ever used a multimeter has 2 leads. You can attach it anywhere in a circuit to measure the resistance, the current, or the voltage across an element. So, for example, if a battery supplies 9 volts, and there are 3 or 4 elements throughout the circuit, not every element is going to get 9 volts of energy, depending on the arrangement, whether it be series or parallel. So one element might get 2 volts, another element might get 3, another one might get the last, last 4 from a 9 volt battery. So in these cases here, we're recognizing that, first of all, V equals IR is one of the laws we're going to use, but what is really important here is if you want to measure the resistance of something, just solve for R. So with a multimeter, okay, even before we had multimeters, you have to do this. So if you do the current and the voltage that's going across an element, you can determine its internal resistance. And what this allows you to do, okay, is allows you to, do more than one thing. To experiment with a product or an item that you're maybe building or creating to get it to be the right resistance, the resistance you want it to be. So this is how you would test it. So you'd have to change the internal resistance of it. So if you wanted a higher or lower resistance, then you could test it by determining the voltage and the current across that actual element in the circuit. Has anyone seen this symbol before over here? You know what it stands for? Omega is the word. Very good. Omega is the word. The unit we're going to use for resistance is called ohms. Okay? Ohms. Based on Ohm's law. So we've got volts equals amps times ohms as far as our unit's concerned. V equals A times omega. Remember, this is not the same as the other omega we looked at. What was the other omega we looked at? We used omega earlier in the year. What was it from? Frequency. Remember that W? That kind of curly W? Okay, this was right here. This is lowercase omega. All right, this represents the frequency of oscillations. Okay, frequency is also used with electrical current. Okay, so you'll see that come up again. But this is capital omega, this is lowercase. Different things. Okay, very different things. All right. With that said, let's take a look at what we're talking about is non-ohmic. So, if you increase the value of, say, the current or the voltage, the resistance of an item should change accordingly if it follows Ohm's law. So if I look at Ohm's law, V equals IR, and say I doubled the resistance and I kept the current the same, I should get double the voltage out. Because I double R, I double V. That's Ohm's law. Well, some materials are ohmic, others are not. And the graph here that you're seeing is indicating the slope of this. So let's take a look. Current is what variable again? I. What's the variable for potential difference? What did that mean again? Go back a slide or two. Where did potential difference come into play? Not Q. Not Q. Nor? Voltage. This is really the voltage down here. So on these graphs, this is from your text. The graphs are illustrating the current versus the voltage. Now, that's fine. I'm going to do it the other way around though, just to show you. But I want you to see both. Okay, so I'm going to illustrate it like this because it, I think, is a little bit easier to understand for ohmic and non-ohmic materials. So they're still going to look the same, but what you'll notice is the slope is going to change. So here, if we still have that, and let's say we still have this one here. If I wanted to solve for resistance, like we did in the last slide, what do you get when you solve Ohm's law for resistance? What did we get in the last slide? R equals what? What is it? V over I. Now, look at this graph here. V over I is really Y over X. Agreed? This is really Y over X. V over I. So if I think about this, Again, the one on the left is ohmic, the one on the right is non-ohmic. If I think about this here, if I wanted to calculate the slope of this line, slope equals change in y over change in x. Well, y is voltage, x is current, so voltage over current is what our slope is. But a minute ago, we defined that as resistance. So the slope of this graph is the resistance. Okay, is the resistance. This is not to be confused with the velocity, position, acceleration graphs. V is voltage. It's a capital V, although it's obviously not noticeable because it's by itself. But that's supposed to be a capital V for each of those labels. So what we recognize is that for an ohmic material, the ratio of voltage to current is always going to be a constant, whatever the slope is. So give me a positive number. What do you got? 21. So the slope of this line, let's say the slope of this is, for example, right here, 21. Well, the slope from here to here is 21. The slope from here to here is 21 because it's a line. And we know lines have constant slopes. But when a line suddenly is curved, which we then call a curve, obviously, what happens to the slope? It what? It changes. So, for example, the slope from here to here would be calculated by what's called like a secant approximation. You'll learn about this in pre-calc next year, but by just putting a line through it. If you want to know the rate of change of the slope between any 2 points, just put 2 dots there and connect them. But if I look and I recognize that when the current is higher up, for higher currents, I'm actually getting what looks like a different resistance now. Look at the red line and look at the black line. Those clearly have different slopes. I don't care what the values are, but I know that they are different. So a material that is non-ohmic follows this parabolic or exponential growth, depending on what it is, I'm not actually certain right here. But the shape is the same, right? So the slope is changing, therefore this has a resistance that is changing. Oops. All right, so traditionally, you're going to use materials that are ohmic because you want a predictable resistance. You don't want the resistance of something to change just because there's more voltage suddenly. Okay, if the voltage and the current both go up, the resistance should still remain the same. It should not change at all. So usually, we're going to see applications where things are ohmic materials. Let's talk about things that affect resistance, not being voltage and current, obviously, assuming that the material is ohmic. There are 4 main things that we're going to talk about. And I want you to give me some reasoning. So read the first one, length. Actually, let's start with the lowest one. It's easier. Start with temperature first. Why does it make sense that the resistance of something changes if the temperature of it changes? Give me an example or explain, either one.
If the temperature is higher, the molecules they have more movement, so and with lower temperature they're not moving as much, so it's easier for the electrons to travel.
That's exactly right. Very good. It has to do with the actual vibrations of the atoms. Higher temperatures, more motion, more vibrations. Thus, it slows down the flow. Okay, it's a higher resistance. So higher temperature. That's what these thermometers are, by the way. You can't see them. This is showing like the thermometer is up to the midpoint, the first one, and here the thermometer is supposed to be up to the top. So what would you write? As T increases, R increases. Right? That's how I would write it if I were taking notes in shorthand, right? As the temperature increases, the resistance increases. All right, that was a good example. How about cross-sectional area, the second one? Explain that one to us, please. Use the image and think about how it makes sense or why it makes sense. And what do you got?
Well, the less resistance, if there's more space, there's less kind of, or there's more room to move about. So.
Exactly. It's like just having more space in a pipe. Think about the fact that imagine you had like this really narrow pipe in your house, which most of your houses do. If you or apartments wherever you live. If you look at the pipe that connects your shower and your sinks to the main outlet pipe to the street, you have like the main outlet pipe to the street is about 4-inch diameter usually, because you have like 5 pipes coming toward it. Those pipes coming through your house are like 1.5 inch, maybe 2-inch diameters, maybe 2.5 at most, but usually not any more than that. So similar to water flow, a smaller pipe, right, with the water would flow a little bit slower through it, it would resist the flow a little bit. So in this case, we're looking at the same idea here. As the wire gets narrower, those electrons or those charge carriers are much more likely to interact with the metallic atoms and thus slow it down. Okay, so again, we have a wider cross-sectional area with less resistance. So what kind of a relationship exists there? Indirect. Good. Indirectly related. As area decreases, resistance increases. The one for material, there's no reasoning behind it right now, but it has to do with the chemical makeup of the metal. But you should know that different materials have different resistances. That's why you see a lot of cables are like gold plated and stuff. It has to do with changing the resistance in the circuit. And the last one, length. Okay, a longer wire just again simply means the same thing. A longer wire means that you're going to have more chance of interaction slowing it down. Okay, so a longer wire, there's going to be a greater resistance. Let's see. All right. Now, a simple, I guess, application of this that I was reading about that I found interesting last year and I jotted down was, have you ever, I hope you have never, but have you ever seen a movie where somebody has like a lie detector test? I was going to say, have you ever been in one? A lie detector test? Now, with a lie detector test, they're testing for many things. It's not just one thing. But one of the things that they do test for is perspiration. Now, why could that be a false negative though? Because clearly, if somebody gets arrested, even if they're innocent, they might be nervous, right? So they might sweat anyway. So this is not like an indicating only factor. It's not like, oh, you're sweating, you're guilty. Obviously, no. But in this case, that's one of the factors they look for. And how can they tell while you're hooked up? They're not like looking for sweat on your forehead or sweat on your body. What they're actually noticing is that your body's internal resistance changes. So when those little nodes are hooked up to your hands or fingers and your head or whatever, however it works, has anyone seen Meet the Parents? Remember when De Niro hooks up Greg Fokker to the lie detector test and straps him in and whatnot? Yeah, that's what I was thinking of with this. So it changes your internal resistance because of the salt. When you perspire, the salt on your skin changes the amount of resistance of your body, therefore altering the current. So the voltage that's supplied is the same voltage. It's a very small voltage. You don't even notice it, obviously. It's not even noticeable in the human body. But the current that's read out is on the level of like milliamps. Well, if they see the current changing, it means that your internal resistance changed. Therefore, that's one indicator to the possibility of somebody lying. Okay, there's other things as well, but this was one of the original things that they looked for. Really simple example. The examples that you really need to know for the test are not going to come until like chapter 20 for voltage and Ohm's law. This is way too easy. Okay, but I want you to just obviously understand that Ohm's law is just simply V equals IR. But we're going to use it a lot further with other applications. So we start with Ohm's law. It says that the resistance of an air conditioner is 21 ohms. So there's a resistance right away. What is the current? So solving for I. When it's connected across a potential difference, meaning voltage, of 115 volts. I might say when it's connected across a battery of 115 volts. He might say when it's connected across a voltage drop of 115 volts or potential difference. Any of those words are the same. What is an indicating factor is clearly the units. When you see 150 volts, that's voltage that you're looking at. Okay, the units should be the automatic factor that you know that it's V that you're actually referring to. So in this case, we have V equals IR. We want to solve for I. So for solving for I here, we've got 115 over 21 equals I, which gives us, what do we have for the current? I think it's 5.5 if I'm doing it right in my head. That's right here. Yeah, 5.5. Okay, so that's the current that's flowing through the air conditioner. Now, something to note. Notice here we used 115 volts, but a minute ago I said these outlets provide 120 volts. So when you're looking at the voltage across an element, that element is not necessarily going to get all the 120 volts. First, several reasons. One, the source could maybe not be providing 120. Second, there could be other elements in the circuit. Third, the wiring in the circuit alone also has some internal resistance. So in these cases, you're not always going to see 120 volts across elements. And Kev, Paul, you guys are working on that project, and you had the multimeter. Do you remember when you used the battery a few times in the beginning? Was it exactly 9, or was it off a little bit still, even in the beginning? What was it at? Okay, something around high 8. So a 9-volt battery that we were using that was brand new, even after initially using it, was already at 8.8. I think over time that would get going down further because we were using the energy. Okay, so yeah, the voltage in the battery changed as a function of time because obviously the battery is using up its energy, using up the chemicals inside of it. Now, when you plug into the wall though, if you took an actual multimeter and you actually used it against the wall here, you should read out 120 volts. Okay, you actually should because you're coming right from the source there. There's nothing that's depleting it or slowing it down. Two things, both theoretical. First, when I shut off the switch, right, the light just turns off. But if I wanted to dim the light, what I'd use is called a potentiometer. And a potentiometer is a way to make a variable resistor. So it uses metal contacts between the two different pieces. So for example, you take the light switch and you rotate it to turn it off, or you lower it down. You're changing the amount of metal that's in contact, and as a result, you're changing the resistance of the element, and therefore the brightness also changes. Okay, the brightness of that bulb changes when the resistance itself changes. Now, another example of that, video games, joysticks. A joystick is sensitive, especially newer games, maybe not old school, arcades, those were pretty basic. But like a new Xbox or PlayStation, the joystick's on them, and you probably know this from any game where you have to aim. If you move a little bit, the aimer will move a little bit slow. If you move the joystick over to the right, the reticle will move much faster. Okay, it's a potentiometer. It's a variable resistor. And the same thing for, I think the last example was a sound, a volume control on a speaker system. Okay, so a potentiometer, it's a special type of resistor that's used widely. And the reason it works is because you have a sliding metal contact that takes on more or less area. Depending on how much area of contact there is, the resistance in the element changes.
So then how does the joystick work if for an older one, but say it moves in like a 360, so how does it change? Or what's the difference between one side to the other side, to the top and bottom?
My guess, it has to do with some sort of electrical field that's established, and then it's read, and then that reading is translated into the actual game. I mean, that's kind of what these LabVIEW things do also. We use them maybe 3 or 4 times this year, most. We use them a lot in my engineering class this year. And when you use them, it takes some sort of a source, and it runs an algorithm to translate that into what is actually being read. So in a video game, there's probably an electrical field that's actually changed or altered when you're moving that joystick. Or, you can probably even look it up, how do joysticks work in Xbox controllers. But it's something to do with something changing that's being read, and then that's translated to the system of how fast the reticle would move. I'm guessing electric field, but I don't know, to be honest now. It's a type of potentiometer, though. That's the idea. Last thing, superconductors. So a superconductor is the idea that, imagine if something can conduct really well. Josh, focus. Stop what you're doing. Imagine if a conductor could conduct electricity very, very well. We call that a superconductor. Okay? A superconductor has pretty much no resistance at all. Why is this important? Let's think. Why is this important? Imagine if you needed to have a circuit where there's a current flowing through it. The minute you remove the battery from it, the current's going to stop. It's going to slow down because there's resistance. It's like flow in a pipe. If you have water flowing through and there's a pump pushing that water along, you turn off the pump suddenly. Is the water still going to flow? No, it's not. I mean, unless you have gravity, unless the pipe is down, but that'd be different. Imagine the pipe is water's flowing up. So this is like turning off the pump, but the water's still flowing. So a superconductor, you can remove the battery, and whatever current was already in the circuit would remain in the circuit still. assuming the circuit is still closed though. The circuit has to remain closed. You remove the battery, but the circuit still has to be closed. So it has to be a setup that way. Now, this is only exhibited below certain temperatures. Remember earlier we said as temperature increases, resistance increases. Well, as temperature decreases more and more and more, resistance becomes almost negligible. Now, what is this symbol represent for temperature? From chemistry last year. Kelvin. What is the deal with the Kelvin scale? Who can explain its use?
Well, there's no negative. And when you get, and it's like a measurement of like how much the atoms are moving. Like, and basically when you reach like zero, that's absolute zero.
And what happens to the molecules when it's at absolute zero? What would happen?
They don't move.
Yeah. Now, the idea is that this is the absence of any molecular or atomic motion whatsoever. That's absolute zero. The Kelvin scale, 0 Kelvin, is really negative 273 degrees Celsius. 0 Celsius is freezing point for 0 Celsius? Freezing point for water. Yeah, freezing temperature for water. So we're talking about a very, 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 very low temperature. Now, we'll talk about this more in heat transfer later in the year, but you can't actually get to 0 Kelvin. Theoretically, think about it. To cool something off, what do you usually do? How do you cool something off? Okay, so the surrounding temperature has to be very cold, right, to cool something off? Put in an ice bath, put in a fridge, put in a freezer. Okay, so if you want to get to 0 Kelvin, what would the temperature of the freezer have to be to get to 0? What would it have to be? No, it'd have to be below 0. But what's the whole definition of absolute 0? You can't go below 0. So if you can't get a temperature below 0, you can't actually get to 0 either. Okay, it's a limit. We'll talk about that later in the year, but this is an example of that now. With this case, what you'll notice is that below 4.15 kelvins, this material that's shown in this graph has negligible resistance. It's not exactly 0, but it might as well be 0. Okay? Now, the part that I find interesting is not this, because this is almost impossible to reach that temperature. You can cool things down to like near 0 Kelvin, but it takes so much energy just to do that it wouldn't be useful. But in more recent years, this is probably like 40, 50 years ago, but in more recent years what we've discovered is that some superconductors can exhibit almost no resistance at higher temperatures than this, which is very useful. Okay? So what I'm going to do is ask you in a second, so you get the idea behind this, below the critical temperature there's almost no resistance, is simply read real quick for about 3 minutes. There's a little documents and handouts real quick. Okay, I'll load it here. The homework's up, but I'll load that document. Spend about 3 minutes reading it, then I want to take a minute to discuss together.